from Hunter College. Today, I'm going to talk about limits. Now, no, we're not in a Calc 1 class. You probably already know what limits are, but just in case you don't, which is kind of concerning, let's do a quick review using the Epsilon and, you can call me black pen, blue pen. No, seriously, black pen, red pen is a great creator. So let's start with the Epsilon delta definition. So, what does that mean? Well, essentially, if we have a function, f of x, and it's groovy like this, then the limit of f of x as it approaches a certain point, and let's say this point has an x value of a, so that means its y value would just be f of a, y value of b. Then the limit of f of x as x approaches a equals b if and only if for all delta and epsilon in the real numbers, for all there exists an epsilon, for all delta in the real numbers, there exists epsilon in the real numbers such that b plus b minus delta, and I guess we should put the plus signs on them too. B minus delta is less than, B minus delta is equal to f of a minus epsilon. B plus delta, this doesn't have to necessarily be positive, is equal to f of a plus epsilon. In other words, that basically means that for whatever amount of precision you want on the x-axis, you can get that precision on the y-axis. So essentially, so let's make this. So as epsilon gets smaller and smaller, so you get closer to this point, the y values also converge on this point. So that's essentially a way to define limits. But not good enough. So let's actually define a limit. Shall we? Let's say we have a sequence, like the harmonic sequence. We know just from intuition that it approaches 0, right? We have 1, 1/2, 1/3, and after 1/2, I'm just eyeballing it. So don't blame me if I accidentally get something wrong. So 1/6 might be somewhere around here. 1/7 over there, 1/8, 1/9, it doesn't even matter from here. So, it should be pretty obvious that it's approaching 0, right? But how do we know it doesn't approach 0.0000000000000000000001? And yes, there is an extremely specific reason I picked 17 zeros. What? Well, how do we not know that it just looks like they approach 0 on the graph, and in reality, they approach this number. It's very, very close to 0. You wouldn't even be able to tell the difference on here, right? Would you? But here's the thing. We need to define something called a neighborhood to understand this. So, the epsilon neighborhood of I'm getting way too used to the Greek alphabet. So the epsilon neighborhood of alpha is all real numbers x such that x a minus epsilon is less than x, which is less than a plus epsilon. So essentially, epsilon is the radius of our little personal space, and a is the exact place where we want to be. So epsilon is this little independent variable, the dependent variable that we're going to change. Sorry, it's been a long time since I took biology, okay? So here, let's say the thing about 0 is it's a very special number. Why? Well, for all epsilon, for all epsilon in the positive real numbers, the epsilon neighborhood, okay, let me think. Okay, for all epsilon in the positive real numbers, there exists n in the sequence, which I guess I'll just call S, such that an actually, wait, okay. There exists n in the natural numbers such that, and we're going to call an the nth element of our sequence, such that sorry, I'm doing this without my notes for like the first time. So n in the natural numbers such that and okay, such that for all x greater than n, greater than or equal to n, ax is in this epsilon neighborhood of 0. Okay, let's put that in actual plain words. So for all possible epsilons, so for all possible radii of our personal neighborhood, so from very big down to the very small, there always exists some element of the natural number of our sequence, some element of our sequence, like 1/2, 1/3, 1/100th, 1/1,000,000th, such that for all x, including that number and after that number, actually I think it's not including that number, ax is in that neighborhood. So what's an example of that? Let's say our epsilon was 1/20. Then, and this is 0, and epsilon can be anything. It doesn't have to be part of our sequence. This is to make things easier on me. So, should be kind of easy to see 1/20 if we extend this over the whole board. Then I'd estimate 1/20th would be about right over here. So, what we're going to do now is we don't have to draw the other side of the board, even though the neighborhood extends over there too. But because this whole sequence is positive, it only does us good to draw it on one side. So here's our little personal neighborhood. So that means that for any x such that ax is less than epsilon, we are now in the personal space. So for example, 1/21, 1/22, 1/23, 1/24, 1/25, 1/26, so on and so forth with the rest of the sequence in hand. So,
you're going to finish it in 10 minutes, right?
Yeah. So what does this tell us? So what does this tell us? Well, if we zoom in really, really far, we're going to see that there's a difference between 0 and 1 times 10 to the minus 17, which I drew right over there. There was some difference. Why? Well, now, when we draw this neighborhood, epsilon can be a real number, which is less than 1 times 10 to the 17. What does that mean? Well, then that means that we have it starts entering the neighborhood, but then at some point it goes past the neighborhood and exits out of it for some epsilon less than 1 times 10 to the minus 17. But that just can't happen with 0. So we want this point of no return in our sequence where right after that element, it keeps going and going and going and going and going into the personal neighborhood, no exits allowed. So we want this personal neighborhood to be kind of like North Korea. Otherwise, there is no limit. So you can imagine it like an asymptote. So once again, we want some point after which, like an event horizon, you get sucked in and the sequence keeps getting closer and closer and closer, but it doesn't exit like this. But does that mean it can't go over to the other side? Does it mean that it only has to keep decreasing or increasing? No, I'm sorry, Dad. Just one more moment. Like, for example, take sine of 1 over x. So as it continues going, and we're just going to ignore 0 because some crazy stuff happens around there. As it keeps going, it approaches 0. But how? Because it goes on both sides of the aisle. Well, at some epsilon, it starts approaching personal space. So we can draw it on the number line just like this. So it goes here, then it goes there, then it goes here, then it goes there, then it goes here, then it goes there, then it goes here, then it goes there. And here is our limit, and our epsilon can be here or it can be here. No matter. There's always some point at which we start entering the epsilon and we never go right out. There's no point at which it goes like this, and then it goes like this, and then it bursts out like that. No, that does not happen. And that is how we know sine 1 over x approaches 0 as x approaches infinity. That is our rigorous definition of a limit in real analysis. Thank you, everybody, for watching, and we'll see you in the next one.